All right, happy Sunday. Welcome back. This is going to be video 5 in our series where we build a vacuum tube guitar amplifier from design to plug your guitar in it and rock the hell out of it. This is where we left off. Right here. We designed the power supply. And then I promised in this video I would tell you how I came up with the 0.25 milliamps for the preamp section, except I have to break that promise because I lied. What happened? I told you 0.25 milliamps. It's actually zero point 0.5 because it is a two-stage preamp. We're using a 12AX7. So now I got to go back and change these numbers here. And there's two tubes, two triode sections in it. So change that to 2.88. And the overall, going to change to 72.88. So the current draw is not 0.25, it is double that, which is 0.5. But I made that mistake for us, so now let's get into how we design and avoid that mistake by paying attention in the first place. Today we're going to be working with VTADIY.com. That is going to be our load line, and I added this fun calculator.net. You can go ahead and make that your favorite if you would like. It is down in the description, or you can pause and get it from here. But let's get into it. First things first, let's open that. And then I'm going to open this calculator because I'm pretty much crazy. All right. So I mentioned that this is a two-stage. We're using a 12AX7. So let us get these triodes loaded, these triode sections. You basically take any triode shape you would like. And then I like to give myself some space and we'll figure it out from there. 12AX7. 12AX7. Way over here. So we can do other stuff. Okay, so now in our power output section, the load, which is 1700, is done by way of transformer, and it's a reactive load. We are going to do a resistive load, and both of these are going to have the same load. So let's figure it out. Let's figure that out first. So if we look here, and we'll show you how to figure out a good load for your 12AX7. So first things first, whenever you punch these in, they've got their own numbers. We know that this is going to be operating at 115 volts because we determined that when we did this in video 4. Right here is going to be 115 volts and is going to be supplying both of those. So once we do that, you'll notice the operating point has disappeared because it's gone negative. But we'll figure that out in a second. First, let's look at this load. Pre-filled out for us, they have a load of 220,000 ohms of resistance. And that makes this red line right here. If we would like that line to be more vertical, we can lessen it. Say, for example, 100,000 ohms. See what that does. And bam, you'll see our load has gone much steeper. Now, the problem with this is when we are making a load line, we want our line to kind of pass through the grid lines here, kind of at an even rate, more horizontal. And as you can see, this kind of is a little too steep. We want a little evener, a little bit more even rate. So we go back here, put back the original 220,000 ohms of resistance. You can see that's it passes through at a much more even rate. It doesn't cut down through, and now our signal will have a chance to be a little bit nicer. So, what does that mean to you? Um, Not much. You can pick any load you want, really. And by changing the load, you're going to change the uh, the current draw here. We have to pick an operating point, but we'll do that in a second. But if you did not have this doing it for you, and you wanted to figure out a load, say you had a from 100 volts, and you were thinking you wanted somewhere in between here, so 100 volts and um, maybe 4.5 milliamps. Well, you could figure that out on this calculator. So you put in the voltage, and what did I say? 4.5 milliamps, or 0.45 milliamps. Make sure you change this to milliamps and not amps. And calculate. Well, it'll tell you that's about a 220,000 ohm resistor as well. If you wanted to do have a lower line or a more horizontal line, then you would reduce the milliamps. Say, let's go to 0.3 milliamps. And now we're at 333,000 ohms of resistance for our load resistor. But anyways, that's helpful. We're going to stick with 220,000. And you'll see that when we do that, we're at about 0.5 milliamps. So we want our operating point in the middle of that, which is going to be 0.25. All right, almost promise delivered. I told you I would show you how I came up with 0.25. That's what I did. And that's how I figured that out. So now we're operating at 0.8 volts between the 0.5 and the 0.1. We're closer to 0.8. And at 0.25 milliamperes, from there we can figure out our cathode bias resistor. But right now, let's put in what we know, the load resistor. Let's add that to our schematic. So 220K, and the other tube's going to get the same treatment. Bam, 220K. And now we got to do our bias calculation. Let's do that, and then we'll add our cathode bias resistor. So let's go back to this Ohm's law calculator. And now we need to put in some different parameters to figure out. So now we've got our grid volts were 0.8, and our current is 0.25. And when we calculate that, we get 3,200 ohms at 2/10,000ths of a watt. Pretty sweet. So now we can go here and make this 3.3K. You can hit this button right here, the flip on the y-axis, and it'll just move everything over to the other side. And this is going to get the same thing. Flip on the y-axis. Okay, now we need the grid resistor. Just like over here, we had 220K for the power tube. We figured that out from the data sheets. I'm going to give you this. It is 1 meg. I always use 1 meg for 12 AX7s every time. You can use 500K if you would like. There's not much of a difference. I prefer this. So let's go and now we got to add 1 meg here, but instead of a regular resistor, we're going to insert the volume knob, which is a potentiometer, is what it's called. That's a variable resistor. So we got this bad boy, and we're just going to call it. It's going to be 1 meg, 1 mega ohm of resistance. Let's go ahead and flip this vertical. And then our grabber tool here, and we'll just put that right there. So this arrow represents what's called a wiper, and this is your resistor. And as you turn your volume knob, this resistor either moves up or down. If the closer the signal path is to this wiper, the louder it'll be. And obviously, the further away, it'll eventually shut the volume off. And what we like to use for these, they have different tapers. And I'm not going to get into that in this video, but we're going to use audio taper. But I'm going to put this right here. So now we've got that. The next piece of the puzzle we have to figure out is going to be the coupling capacitor. Now, over in our power supply, we had decoupling. We wanted this 128 volt stage to be decoupled from this 115 volt stage. And we did that with resistor and capacitor. We're going to do kind of the opposite here. We're going to do a capacitor resistor, and it's going to couple it. And how does that work? The signal comes in here from your guitar when you strum it, goes into this tube. It's an AC signal, and it comes out a larger signal through here, and it's actually superimposed in here, and it's a larger signal that you see come out here. And what the capacitor does is it blocks the DC, the volts DC, which are going to come out of here into this one and this one. It blocks that, so only the AC signal can come through and then go into the next stage and then do the same thing and come out even larger. And then we'll need another capacitor to couple to the output stage. So let's go ahead and figure that out. We do that by this wonderful formula right here, the reciprocal of 2 times pi times frequency times resistance. Don't let it scare you. I'm going to step us through this. So in this particular case, our frequency is going to be 20. We want 20 hertz. That's pretty much the standard. That's what you want to flow through there. When you're talking about a bypass capacitor like this one, which uses the same formula we're going to do, we're talking about 10 hertz. But right now we're coupling, so we're talking about 20 hertz. So let's do it. It is 2 times pi times our frequency, which is 20 hertz, times the resistance, which is 1 mega ohm, times 1 million, equals that goofy number. And then we hit our reciprocal button, and it gives us that. Now to bring it into microfarads, we just multiply by 1 million. And boom. So the most common capacitor in microfarads is to 0.0079 is going to be 0.01 microfarads. So let's do it. Let's get this guy 0.01 microfarad, and that, tip it over like that. And all our coupling capacitors, I like to use a specific capacitor, orange drops. And the series I like is a 600 volt. So these will all be 600 volt capacitors. You could use other if you like, as long as it'll pass at least 120 volts. So let's talk about this next capacitor here. So our next capacitor has to go couple from here to here, and it sees 220K. So let's go ahead and do that calculation. So we have, once again, 2 times pi times our frequency, which is 20 hertz, times 220,000. And that gives us that goofy number. And then we hit the fun reciprocal button, and it gives us that. Now we can multiply by 1,000,000 to bring us to microfarads. And there we go. The closest common value capacitor-wise to this is going to be 0.033. However, another close value, 0.047, is what I'm going to choose. And the reason I'm going to choose that is it's going to let me allow for slightly lower frequencies to pass, but not too low that we're going to introduce noise. So there's that capacitor. I'm going to put that there. That there. That there. And I think I'm going to move this whole section. If you just click, you can highlight everything and bring it in. Just going to move that up a little bit further. And now we can wire up, actually. Move that down just a smidge. So before we wire up, let's bring this entire thing and connect it right there. Kind of smashed. There we go. All right. Now let's wire it up. So that to that. Grid to grid. This to this. And all of these get connected together. This is the ground. And I'll show you how you know which ground is which. So anything that's powered by this 128 volt section is going to get grounded to this. So the plate and the transformer both have 128 volts. The grid, the input grid, shares 115, and that is going to power everything in this section. The input grid number 2, and this capacitor and this resistor, all sharing this ground right here, this point. And the preamp section is all powered by this point right here. So let's wire in the power section for that real quick. And to do that, we're going to need some jumpers. And put them vertical. There's one. Put it vertical. Here's 2. Put it vertical. then we just move them where we need them. So there's one right there. Oh, that's not what I want to do. I'm going to put it here, but I'm going to move this over so we don't get confused. And then the other one I'm going to put right here. And the reason for these jumpers, is we don't want to get confused about what's getting wired to what. We want a wire not connected to here or here. So let's go ahead and wire that up. Through there. Well, it is not doing what I want it to do. Maybe we'll start from here and go down there. There we go. There. And then to there. We got to move over that 1 microfarad. It's getting pretty cramped in there. There we go. But we know what's what. Okay, and that is it. The only thing I will say is you'll notice we don't have bypass capacitors for either of these cathode bias resistors. And the reason for that is this resistance is quite high for a cathode bias. And if we do our calculations, which when we're doing bypass caps, it's 10 hertz compared to 20 hertz that we did for the coupling capacitors. But it's that same calculation, 2 times pi times 10 hertz for the frequency times the resistance. And then, of course, we hit the reciprocal. Except I did something silly, so we got to do it over. 2 times pi times 10 times 3,300 equals reciprocal button. Now we multiply by 1 million to bring us into microfarads. Okay, 4.8 microfarads. So that isn't going to make very much of a difference. And you'll see that the lower the resistance, the higher the microfarads, the higher the capacitance. So the only thing we'd really be doing by adding capacitors here is we risk introducing more noise into our circuit and possibly overloading, which when you turn your volume up, if it's overloaded, it's never going to go to full volume. As you go to full volume, it'll actually start getting quieter, and might have a little bit of a fuzzy sound to it. So some guys would go ahead and add it. I'm not going to. Some guys might just add it to this. Another reason I won't add it is because it reduces the gain just a little bit. I mean, you won't be able to really hear much of a difference. But there's already not going to be a whole lot of clean headroom in this amp. As you turn it up, it's going to break up and give you that natural tube crunchy distortion. So there's not going to be much clean headroom. And we can get a little bit back here maybe. Maybe not even noticeable, but I think this will make overall for a nicer circuit. Okay, well, thanks for watching along. If you have any questions, please ask me. In our next video, we are probably going to try and finish this up. We got to add the tube socket numbers to the electrodes in the tubes here and here, and we got to have an input right here, and then we have to wire up the heater. So I don't know if that's going to fit in one video, but I'll try and do that. And then after that, the next thing we got to do is we got to start figuring out a layout. And I will put out a parts list, and so you can order and build the tube amp along with me. So I'll see you next time. If you have any questions, go ahead and ask me. And have a great day. You guys all rock.